and we'll begin. So, vector proofs, right? If you look at the textbook, there's only 5 questions, and it's not enough because this is a very important part of the course. So I've supplemented it with some questions from previous textbooks. So our plan today, we're going to go through the examples on page 20 and 21. We've also got 2 exam questions either side, which we'll leave for now. And we'll get you guys to get started on question set 1. So it'll start easy and then it gets progressively harder. There are some very challenging vector proof questions. So it's really important that we master the basic skills and then progress on to the more challenging ones. Let's get straight into it. What we have here is we have 2 vectors. We've got vector OA, which we've defined as vector A, and the vector from O to B is vector B. And we're saying M is the midpoint of AB, and we're asked to prove that vector OM, the vector from O to M, is half of A plus half of B. So we've got to demonstrate that that's true. So the first thing we want to do is we want to come up, well, what is vector OM? What is a relationship we can use to describe it? So vector OM is equal to the vector from O to A plus the vector from A to M. Okay, that's very clear. Vector OM is the vector from O to A plus the vector from A to M. And we know vector OA can be expressed in terms of A. So now we just need to find, well, how about the vector from A to M? So let's come up with a relationship for vector AM. Vector AM is half of vector AB. All right, it's halfway between, it's the midpoint of vector AB. And so then we're going to come up with a description of the vector from A to B in terms of A and B. So the vector from A to B, one way we can express it is minus A plus B. If I flip that vector, we're going from point A. Minus A plus B takes me from point A to B. So vector A from A to B can be expressed as minus A plus B. Okay, now let's substitute that into here. Or maybe I'll simplify it a bit first. We have minus half A plus half B. Now we'll substitute it into here. So we have plus minus half A plus half B. And this will simplify to be half A plus half B QED. I'm going to shut the door because they're noisy. Alright, everyone okay with the first proof? Very good. So let's move on to the second one then. We have OABC is a rhombus. Okay, so firstly that means that all of the sides are equal in length. It's a square that's been tilted. Now prove that OB is perpendicular to AC. OB perpendicular to AC. Prove that they meet at 90 degrees. Now, it's going to be perpendicular, the property we're going to use, it's going to be OB is perpendicular to AC if OB dot AC equals 0. So that's the property that we're going to apply. Now, we're going to be a bit creative here and come up with some vectors. So I'm going to define the vector from O to A as lowercase a. Now the reason we do this is because if OA is A, then CB is also A. It's parallel and it has the same magnitude. So that's the reason we express them in terms of a different character, such that we can describe like relationships across the shape. And we'll define AB as vector B. Okay, the vector from A to B as vector B. Okay, now what this is going to give us is now we have a relationship for OB, because we're interested in vector OB. Vector OB is just going to be vector A plus vector B. Alright, so we've got vector OB. And we want to know vector A to C, the vector from A to C. So starting at point A, I would go minus A and then plus vector B. Minus vector A plus vector B, that's going to be the vector from A to C. Minus A plus B. Okay, so then if we're going to perform OB.AC, we're going to have, so let's write it like this, OB.AC, that's equal to A plus B dot minus A plus B. And we can use the distributive law for a dot product. It's going to be minus A dot A plus A dot B minus A dot B. I'll just say very quickly, A dot B is the same as B dot A. Alright, so I'm just putting the A term first when we do that one, and then plus B dot B. Okay, A dot B, take A dot B, we cancel, and so we're left with A dot A plus B dot B. Now, one of our properties of the dot product, so whenever we're getting something like this, it's helpful to reflect on the properties of the dot product. So they are listed on page 10. I'll just back a few pages. I'll point out this one to you. A dot A is equal to the modulus of A squared. All right, so here we have minus the modulus of A squared, and here we'll have the modulus of B squared. Now, because it's a rhombus, the modulus of A is equal to the modulus of B. So we can write that because rhombus mod A equals mod B. So we have the modulus of minus A squared plus the modulus of A squared, which equals 0. Therefore, OB perpendicular to AC. So that's question 1 and 2. Everybody okay so far? Okay, we're going to prove the midpoint theorem. So we have this set up here. A, B, C, D, E. Alright, prove that the line joining the two midpoints of a triangle is parallel to the third side and half of its length. So, the two midpoints are here and here, so that means this is equal to this, and this is equal to this. Okay, so D is halfway between A and C, E is halfway between A and B. And we want to prove, what we're trying to prove is that DE is parallel to CB and half of its length. So what we're going to prove is that DE is equal to half of vector CB. And prove that this relationship is true. So let's just start by defining some vectors. All right, so I'm going to go let the vector from A to D be A. Okay, so if A to D is A, then D to C is also A, and the vector from A to C is 2A. All right, I'm also going to define the vector from A to E, and I'm going to call that vector B, and so that means that one would be vector B as well. Now the reason I'm not defining vector DE is because that's the one we want to discover a relationship about, and we don't want, like we can express, now that we've defined this vector and this vector, vector DE can be defined in terms of A and B. And so we don't want to create an unnecessary third variable. We can define vector DE now in terms of A and B, so let's do that. What is vector DE? The vector from D to E is going to be minus A, so we're flipping A, and plus B. All right, from D to A is minus A, and from A to E is vector B. So we have vector DE. Okay. How about vector CB? Now that we've defined it, vector CB, the vector from C to B is going to be minus 2 lots of A, and then plus 2 lots of B. And we can see that this is equal to 2 times minus A plus B, which is 2 times vector DE. All right, so we have CD equals 2 times vector DE, so we have half of CD equals vector DE. QED. All right, number 3. We have a trapezium. So we've got A, B, C, D, M, N. All right, in the following trapezium, the length of AD equals 3BC. Okay, so I haven't drawn it very well to scale, but BC, AD is 3 times BC. Maybe I'll just fix the scale a bit so we're not getting too confused. That's probably better. M, B, AD. Good. All right, so let's define a few vectors. Firstly, like if we define the vector from B to C is vector A, right, that's A, then the relationship we have is that this is 3A. The vector from A to D equals 3 lots of A. Okay, and we also have, it is the midpoint, so this magnitude is equal to this one, and this magnitude is equal to this one. All right, and so let's, here I've got let, and so we'll have vector Bm can be vector B, and we'll have vector Cn can be vector C. All right, so we've introduced a few variables here. Now we're trying to come up with a description of vector Mn. We want to know what's the value, let's read the question. Find K such that Mn is equal to KBC. We're saying what's the relationship between Mn and BC? Now they're parallel. Okay, they're parallel, so we're going to try and find this number that describes the relationship between them. All right, so let's then, what we're going to do is come up, well, what's a way we can describe vector Mn, the vector from N to N. So at the moment, we've got the vector from B, that's vector B, and we have, that's vector C. So if I'm going to describe the vector from M to N, I'm going to say minus B plus A plus C. All right. Now, we haven't really got much to go on there, so let's try and use some of the other relationships we have. Like for instance, this one AD. The vector from A to D, all right, one way we could describe that is we've got minus B plus minus B, so we've got, you know, minus 2B plus A plus 2 lots of vector C. All right, and so this is going to give us, so minus B plus A plus 2C, so I've just described it there in terms of B, A, and C. Now we know that that is also equal to 3 lots of A. Okay, that's the definition we started with. That's vector A, this is 3 lengths of A. And so what I'm going to do is take away A from both sides, and we have this relationship, right? Minus 2B plus 2C equals 2A. All right, now, just be careful because we've said vector AD is equal to this, all right? But now that I've changed which is equal to this, And so then I'm just focusing on this relationship, and I've subtracted A from both sides. So vector AD is no longer equal to this because I've gotten rid of the A. I'm taking this relationship and manipulating it, right? So that's equal to 2 lots of A, and so what we have here is we have, C take away B is equal to A. All right, so we have a relationship for vector A. Now let's plug that into our description of vector Mn. All right. If we look up here for vector Mn, we can see we've got C take B plus A, and I've got another lot of C take B going there. So I'll write that down here. Vector Mn. I'm plugging that C take B where the A is. So I've got C take B plus C take B. This gives me 2 lots of C take away B. Now C take away B is equal to vector A, right? So we've got 2 lots of vector A. So we can express it like that. And vector A is the vector from B to C. So it's 2 lots of vector BC. Now we'll answer the question in a moment, but basically, if this is A, this is 2A, and this is 3A. Now we're asked specifically, what's the relationship between MN and BC? Oh, we've expressed it. MN equals 2 lots of BC. So the value of K is 2. Okay, so that one's a bit trickier, and I probably took you on a bit of a roundabout trick to get there. But let's just explain how did we go through and solve this. So we started with the definition that if that's 1 length, that's 3 times the length. All right, so we said that's vector A, that's going to be 3 lots of A. We could find this is vector B, that means this is also vector B because that's the midpoint. This is vector C, that's also vector C. And then we started saying, how can I describe vector MN? How can I describe vector AD? So the vector from N to N, minus B plus A plus C. The vector from A to D, minus 2 lots of B plus A plus 2 lots of C. So that's that expression there. But then we also said this has a relationship to A. In fact, this is 3 lengths of A. And so then we took that relationship and we've manipulated it to come up with C take B is equal to A. Okay, we now have a description of A. We plug that back into vector Mn, and we see vector Mn is 2 lengths of C take B. Vector Mn is 2 lengths of A, which is 2 lengths of vector BC. All right, so that's enough for us to get started. So question set 1, which is in your notes book. So we won't be looking at our textbook today. The order we'll do it in, I'll basically say we'll go straight to the question sets, and once you've completed the question sets, then you can have a look at the questions in your textbook. Very good. All right, so let's get started. Question set 1. That's our plan for today.